All right, good afternoon, everyone. Welcome back from lunch. We're into the home stretch at Drone Enable 2. Our next session looks at very high altitude operations. It examines what lessons or best practices from UTM can be applied to the management of high-level airspace above current commercial flight trajectories. Our moderator for this session is Miss Nancy Graham. She's the president of Graham Aerospace International, a former senior executive with the FAA, and my immediate predecessor as the director of the Air Navigation Bureau of ICAO, now consulting to new aviation entrants and challenging all of us in the regulatory community, just like she has been doing ever since I met her over 25 years ago, with why not? Why can't we do this? And when people tell her, well, these are the reasons why, she says, well, let's solve for that. So one of the foremost problem solvers that I've ever met in aviation, Nancy, the floor is yours.
Thank you, Steve. Thanks, everybody. I hope you had a good lunch. Certainly was a lot. So I want to take you a little bit on my personal journey, and why it's relevant is because I've changed what I think about what we're doing today because of what I've seen and what I've learned. So like Steve said, I started the RPAS work in 2007. Yes, Leslie is the one I stuck with the job. She stuck to it, God bless her. And during the ICAO assembly in 2013, I had proposed some specific work on small UAVs. And the ICAO assembly did not agree with that. So you heard the result of that. And I have to tell you, for a little while, I was kind of mad about that, because I really felt like the work needed to be done. But when I look back now, that actually may have been a blessing, and let me explain why. Because that didn't happen, JARIS was formulated. So JARIS came into being because ICAO didn't take on the work. And I have to say, JARIS has done an amazing job so far. Some of the work is a little over-engineered. We've talked about that. But that's part of what we learn as we go through the process. But I want to congratulate JARIS for the work, for being willing to take it on, and for the work that they've done so far on behalf of not just Europe, but of the aviation community as a whole globally. So I congratulate you for that. Then the last work that I did was an RPAS symposium in 2015, and the word symposium has no specific meaning, and that's a good thing. Because if you've worked with ICAO, you know it's full of rules. And I didn't want any rules. I wanted to be able to talk freely, without a lot of political interference, about what was needed for the aviation community going forward. So I thank Steve for continuing on with this work, and particularly for being the initiator of the Drone Enable, which is how to have this open conversation about what's needed for the future and how we do it together. So I left in 2015, and if you'd asked me in 2015 that we would be here where we are today, talking about what we're talking about today, I would have said, no way. And if you'd asked me 3 years ago, even if we knew the term UTM, could UTM possibly be as safe as ATM? And I would have said, no way. And now I say, not only can it be, but it has to be. Because ATM is continuing to change every day with the continuous increase in what we know as travel, and we know that that only brings us challenges for the future. So UTM has to solve that. And I personally believe that UTM will become the ATM. So what we're talking about in this panel is high altitude. Earlier, so if I can go ahead and put up the slide next. Oh, I'm supposed to do something, right? Move this. Maybe? Try the next one? Okay, somebody thank you. So what we traditionally talk about, and our traditional focus, is where we have transport aircraft. And over the last couple of days, we've been talking about the low altitude and the focus on UTM for the low altitude, and in some cases how we transition to ATM. And there's no question that that's a more difficult challenge. What I want to talk about now is the new entrants in upper airspace. What you may not know, and there's not quite as much noise about that, and frankly I think that's a good thing, I think there's a tremendous opportunity. In fact, it's our responsibility to create the same level of DNA for UTM as lower as what we have in upper. We will do a disservice to the aviation system if we don't have the same kind of thinking and the same kind of DNA from lower to upper. Regardless of what we call it, whether we call it UTM or ETM or whatever we call it, it has to have the same DNA and the same kind of principles. So what's different about high altitude is a few things, but there's some things that have been settled legally that I want to hit. First of all, high altitude prior to space belongs to ICAO. That's been settled. There's no question about that. That is ICAO responsibility, and it is state responsibility. There's no question about that. Do we need any additional changes to the convention or changes in any of our instruments? No, none of that needs to be done. We can do what we need to do in high altitude with the existing structure that we have today. In the high altitude, what you have is a whole lot of different capabilities of different craft that operate differently, but that will loiter for long periods of time, and we'll get into that in a minute. So this session is really about how do we learn what we're learning quickly in UTM and apply it to upper, and how do we have that same level of DNA so that what we have is an overall integrated aviation system for the future. To begin the discussion, I'm asking Reinaldo to come back. Reinaldo is, you heard him in the last session, he's the UTM manager for Wing. He's also working very cooperatively with the other company that used to be a Google company, now graduated, called Loon. And he's going to share a little bit about how Loon works and how they're working together on a combined and integrated UTM. Reinaldo?
It's pretty fabulous working in Rails, where we have Waymo, the self-driving car, Loon, the high-altitude balloon, which we'll learn a lot about, and then, of course, Wing, all in the same building. It really reminds you of what's coming next. But if we can go back to the previous slide just for a second, it's important to, I seem like they're all flipping through rather quickly. We can go back. Let me see if I can get this to work. Great.
Granted, large parts of the world are still unconnected. In big towns and cities, providing connectivity with cell towers is economical, as there are lots of people there wanting to connect. But the further away from these towns and cities you go, the fewer people there are, until eventually connectivity just stops. To bring the internet to people in these areas, we need to look up, way up, into the stratosphere. From here, we can provide connectivity across much larger areas, bringing the benefits of the internet to more people. So how do we get there? With balloons. Really big balloons. Beginning their journey from one of our custom-built balloon launchers, our balloons are filled with lighter-than-air gas and released up into the skies. Rising 20 kilometers into the stratosphere, Loon balloons float twice as high as airplanes, well above weather and wildlife. To get to where they need to go, Loon balloons sail the winds by moving up or down into different wind currents traveling in different directions, joining other balloons in small teams over areas where connectivity is needed. Ground stations connected to local internet service providers send signal up to the balloons and then back down to the ground over large distances, allowing people to connect directly to the internet with an LTE mobile phone. When it is eventually time for our balloons to come down, we navigate them to remote areas and work with local air traffic control to manage their slow descent down to Earth, where they're collected by our recovery teams. By repeating this process at scale, we hope to provide continued connectivity to users on the ground, bringing the internet to more people in more places around the world.
From a personal perspective, I've actually seen Loon touch my life. When Puerto Rico experienced a very intense hurricane that knocked out most of its cell service, Loon was able to provide cell coverage for Puerto Rico. And while it's hard to tell exactly, but I'm pretty sure my family, actually my Puerto Rican side of the family, actually got reception there. And it's pretty amazing that we were able to do that as a company in such a short order from when the actual incident occurred. And the same thing actually happened in Peru. When Peru had large flooding, and you might have heard of this as well, we were able to use balloons to augment the service there and continue to provide and support search and rescue, as well as various people reporting their safety. And And so even in that humanitarian side, it's been great to show how quickly balloons can react and provide those services. But talking a little bit about more of what we're doing on the Loon side with ICAO, definitely focused on being able to show how we can operate at flight level 600 and above, how we can do industry-based cooperative separation, and the FAA has been very supportive in planning to use that. And we're working on an initial industry plan, of course, to how to do that cooperative upper UTM testing, and of course working very closely with ICAO with those ConOps to make that happen. A little bit about the operations itself. We exceed kind of the ICAO standards, and as part of that, we make sure we have an ICAO-compliant SMS in place. That's a great way for us to monitor the safety as part of Loon operations. They've flown over 800,000 hours and over 29 million kilometers. As you saw in the video, it navigates with wind currents, and we've really changed a lot from that initial pre-2016 steering concept. In the bottom left, as you see that very tight band we'd be, we learned a lot with the winds, and you can see us taking off from the US, flying across South America, across the ocean, and then providing services in Africa, as the balloon you see that was flying over Nairobi. Really a global operation in multiple countries that you're flying over as part of that. A little bit, I'm not going to go through all of this, but there's tons of command and control processes that work in Loon's balloons. There's redundant comms, automated navigation. We'll talk a lot about this, but it's not, there's a lot of machine and learning and probabilistic trajectories that go into this process, and that's all automated. But of course, there's a way to fully override and have automated constraints. Health monitoring on board is a key piece, and there's, I think, 2,000 sets of telemetry data per minute that's shared to help monitor and be part of that process. Of course, they're focused on NOTAM displays, airspace activities, being able to have that global airspace picture for the area they're operating, and trajectory simulation to really understand what are the potential outcomes so we can see what the reaction is. And on the right, you see a picture of kind of their monitoring system. Loon flies always above traffic and clearance and has focused a lot and innovated and have harnessed the wind to go ahead and make sure we stay in that altitude boundary above the ATC clearance level that they've worked with that country on. And so you can see, even in that entire flight, the one that went to Nairobi, that it's always stayed over the 50,000 feet level, and has done that consistently, even though it's ranged between 50,000 and 65,000. And that's a key piece for our operations to stay above traffic. One of the ways we do that is by enabling precise altitude control and monitoring. So of course that can be adjusted by the clearance in the area that's operating in, and there's health monitoring, as we talked about, that sounds alerts if we're close to a clearance in any way. But the key thing here, and it's actually a small footnote in the bottom right, but it's we're able to maintain altitude within plus or minus 400 feet. And that's really a very precise system as part of that, especially using kind of the ballast to maintain the altitude and the pressure, et cetera, as part of it. The other key piece is we have several ways to manage automated airspace avoidance. One of the best ways, of course, is to fly over it, given the level of vertical control that we have. And so we generally fly over prohibitive airspace if that's a potential option. And then there's also ways to do horizontal avoidance. However, since we fly with the winds, sometimes that can be a very wide swath, and if we have to avoid, as you see in this picture, prohibited airspace, we can't actually access or provide service in that gray area back there because we have to use the winds to kind of navigate around, and you see that kind of elliptical shape as part of it. And so again, vertical avoidance for Loon balloons is always preferred, but there are ways, and even though it's a very wide way, to do horizontal avoidance. And the key piece here, right, is the focus of flying high enough and having minimal to no additional workload for air traffic at those levels. Here's an example of all of our trajectories since September 2017, or actual ones. And as part of that, you can see, one, that global perspective, the wide range at which balloons travel, and honestly, the fact that as a fleet, it's managed with that kind of self-separation. Right? For us to provide, as you saw in the video, that continuous service, you need to have multiple balloons in that area. You need to be able to add balloons as needed to provide that coverage. You need to make sure, of course, they're separated from each other. And as we talked about, of course, we're always above traffic. One thing that's been interesting, and you'll see that third bullet, we heard this other spots, radar clutter and noisy proximity can be, and in some areas have been achieved by filtering out high altitude traffic or balloon transponders. And we think that's an interesting piece. In some cases, it's just not helpful to have it on the display. And so with that said, I think that's a good summary of kind of our Loon operations. We'll talk a little about it in reference to UTM as well, but I'll hand it back to Nancy. Thank you.
Thank you, Reinaldo. So Loon is one of the first to market, and another of the companions is Zephyr. And Andy Tailby is the head of operations for flight operations for Zephyr, and he's going to talk a little bit about Zephyr and some very recent tremendous success that they've had. And I will say that what you saw in Reinaldo's briefing is about industry-based cooperative separation, which implies that industry is going to work together to create a UTM that's automated at that level. So with that in mind, we have an operations working group of which Andy is a member, and we're working very closely together on how we make that happen for the future. Over to you, Andy.
Thank you very much, Nancy. You heard about Loon from Reinaldo. That's one way of accessing the stratosphere. We have a different way of accessing the stratosphere. The motivation is largely the same, in that we think that that is a place to put persistent platforms that can carry a variety of payloads. Zephyr is an example of the diverse craft that will be flying in the stratosphere in the future. And that's a really important point to bear in mind when we get on later to talk about UTM and how we have to deal with a variety of different characteristics. Some of those characteristics make them a challenge for air traffic management. Some of them actually make this type of craft quite amenable to air traffic management. So I want to go on to just describe some of the characteristics of Zephyr in that context in order to help you understand how that might work. So the first thing is, what is Zephyr? It is a 25-meter span, very lightweight, solar electric powered, high altitude, very long endurance unmanned aircraft system, or remotely piloted aircraft system, I should say. We are designed for about 90 days of operation with the current technology, and as you can see there, we have already demonstrated this year a continuous flight of just under 26 days. Sorry, Dirk, we should probably have gone round once more to get the last 3 minutes, but there you go. 25 days, 23 hours, 57 minutes, there you have it, for a variety of missions. So the key point about Zephyr here is that fans of Flight Radar 24 will appreciate that not only did we stay in our assigned altitude band, broadly speaking, 60,000 to 65,000 feet throughout the majority of that 26 days, and only when we deliberately chose to fly in a different altitude band did we do so. We also successfully contained it and maneuvered very precisely within a defined volume of airspace, and we also were able to overfly some pretty inclement weather without any particular problem, thus demonstrating the robustness of this sort of platform once it gets up into its happy home, which is in the stratosphere. You can see from the infographic there that we address a number of mission types. We are payload agnostic, and we can therefore address a number of sectors as far as our customers are concerned. The most significant being, as Reinaldo alluded to, the ability to provide services to regions where there is connectivity services, to regions where there is relatively little terrestrial infrastructure. So let's just talk about the ConOps of Zephyr. How does it work? Well, the first thing to bear in mind is that it is solar powered, therefore, unsurprisingly, it needs sunshine. And we describe our core capability as a year-round capability within a certain latitude band of the equator where the sun is shining. But we also have a high latitude, more seasonal capability, which means that we can pretty much cover the entire surface of the Earth, albeit not necessarily year-round. And our concept of operations is to have a relatively few strategic operating bases around the world at low latitude in order to assure their availability. We are equipped with beyond radio line of sight communications. We have a truly global capability. And although we're based on traditional ground control stations at the moment, we will ultimately have a centralized mission control center. So the concept of operations is like this. We would launch from one of those low latitude operating bases and climb basically in the overhead into the stratosphere. We then move the aircraft to the mission area at something like 1,000 nautical miles a day. Now that may not seem like a very spectacular rate of progress, but of course if you can stay airborne for 3 months, then a few days to transit to the mission area is perfectly manageable. If we need to maintain a capability for even longer than the endurance of any individual RPA, then we can, of course, shuttle additional ones and take over the load. Now, Zephyr is necessarily very lightweight. It achieves its amazing performance because of a confluence of modern technologies, if you like, that brings everything together to achieve the efficiency that we need. There are some consequences of that. The first is that it flies very slowly, so 40 to 50 knots true airspeed when in the stratosphere. Limited maneuverability, we can turn on a sixpence, but that's the point. It turns on a sixpence and just changes its heading. It doesn't actually go anywhere. Low rates of climb and descent, order of 100 feet per minute. And we can be affected by the wind when we are at tropospheric altitudes. So it is possible that during the climb and the descent, it may not follow the precise track that we had predicted. So it's obvious, I think, that it is not capable of conforming to normal IFR expectations, normal ATM expectations, when we are in the ATM zone, if you like. But the key point for Zephyr is that for 99% of the time, just like balloons, we are above normal air traffic, comfortably above normal air traffic, operating in that sweet spot above flight level 600. So the reality is that we are preparing for operations, regular operations in higher airspace right now. And the accommodation of systems such as Zephyr is a very real possibility very soon. And like a number of other technologies that we've discussed this week, this is happening now, and we need to take that into account and move forward in order to enable us to open up this exciting sector of aviation. We are preparing for regular operations in Australia, and we've been working with CASA, exploring the limits of the SORA process and applying it to this novel type of system, for which it probably wasn't originally intended, but for which it is showing considerable adaptability, and that's great. I would also say, Scott, that it is good to be working with a forward-thinking regulator who can move with us in order to develop novel ways of operating. Now, why is it possible to accommodate Zephyr in the current airspace management system? Well, the first thing is we're pretty antisocial, actually. We don't need or indeed desire to operate near conventional aviation. So to that end, we will choose to put our operating bases a long way from busy airports, and we will choose to put our climb and descent areas away from relatively busy lower and upper airspace. I should also add that in all of this, our electronic conspicuity is normal. Another advantage that we have is that nothing happens quickly with Zephyr. Plenty of time to think about what's going on, to predict the trajectory based on the conditions of the day, and to communicate that information to all stakeholders. It therefore transpires that the climb and descent can be managed quite adequately using normal ATM practice, although there may be some bespoke elements of how we separate from other traffic. The other key point, handling the exceptions was a term that was used recently, is that we can predict and mitigate abnormal situations way, way in advance. Most of the issues that can arise with Zephyr will result in what we call a gradual loss of flight performance, which will take course over hours, possibly days, before it has any effect on other airspace users. The other key point is that, at risk of stating the obvious, certainly right now, there are not very many other people flying up there in the stratosphere. Now, we don't take that lightly, but we do acknowledge that the traffic density is very low, and therefore that forms an intrinsic part of the safety argument for Zephyr. We will remain above what we term the deconfliction flight level, which will be chosen according to the circumstances that we're flying in, and that is the deal that we will do with ATM below us, that we won't appear in your world unless we give you lots of notice. So what would be the enablers then for sustainable higher airspace accommodation for systems like Zephyr? Well, the first thing then, as we are doing in Australia, is to work with air traffic authorities and air navigation service providers to be able to get up the elevator and get down the elevator relatively safely and easily, and to quickly establish whatever temporary arrangements may be necessary to allow us to climb and descend. Flexibility, therefore, is what we need in order to enable us to choose suitable launch and recovery opportunities in weather that will assure our ability to stay within whatever airspace we have been assigned. The other important enabler in this respect is that although we don't expect to come down, it is a possibility that we might. We therefore need to have a mechanism for being able to handle those exclusions, and we've been able to work that out in Australia with Air Services Australia to good effect. We clearly need to be able to define where we can go based on real-world traffic patterns, and generally speaking, that means agreeing what the deconfliction flight level is and what that buffer level is between how we operate and how other aircraft operate. And we have discussed in the ICCAIA Upper Airspace Working Group how we prefer a user-centric way of deconflicting traffic in the stratosphere. Initially, it might look like a sort of time-bounded booking of airspace volumes, but very rapidly, this is going to move to something that looks remarkably like UTM. And it becomes very apparent that most of the principles of UTM, and hopefully some of the tools that UTM will exploit, are equally applicable to operations in the stratosphere for vehicles like Zephyr and Loon. We have an additional challenge which has hitherto not really been acknowledged fully as part of the RPAS paradigm, if you like, and that is that we are truly capable of global operations. We therefore absolutely need to tackle the challenges of international flying, of crossing FIR boundaries, and of crossing state airspace boundaries as well. And the evidence so far suggests that current practice is to establish a number of bilateral arrangements with many states, a challenge that Reinaldo recognises only too well. And that can be a problem, because everybody does it differently, slightly differently. You can apply the same principles, but everybody has got a slightly different requirement, and the problem needs to be tackled in a slightly different way, which means that you end up with a multitude of bilateral agreements which are no use to anybody, really. They cause everybody a lot of work, including ANSPs, regulators, and indeed us. So, moving forward then, and in the context of UTM, what might be the next steps in order to enable craft like Zephyr to operate in the stratosphere readily and to do so with minimal impact on anybody else and in a relatively efficient way from a procedural point of view? I'm postulating now that we should draw on the experiences of all the work that's going on into LUTM to develop HUTM, a new paradigm for higher airspace. Same principles, different kinematics fundamentally, but we've got to remember that although we're talking about relatively low energy systems today, in the fullness of time, there will be manned aircraft moving extremely quickly relative to Zephyr and Loon, and we do need to take those things into account as well. I also think that we need to be able to define in a universal way that interface between our HUTM and relatively conventional ATM for the climb and the descent. And above all, we need to be able to accommodate international flying in a relatively straightforward manner. We're making progress. We have a paper going in at the Air Navigation Conference this year, which captures all of the principles that I've talked about, and the paper is called Imaginatively Operations Above Flight Level 600. And we're proposing in that paper a collaborative effort between ICAO, industry, and states in order to address global higher airspace procedures. We aspire to gather real-world data to support UTM adaptation, and we're looking forward in Australia to working with our colleagues in Loon to take the first steps to understand how exactly that might work in practice, thus starting, Mike, to gather data that you so yearn for, and we understand that. And we're all working together through the ICC AIA collaboration to accomplish that. So we're on the cusp of a fantastic development in aviation, our ability to persist in the stratosphere, and the opportunity really does exist right now to learn safely from accommodated higher airspace operations, so that when in the future it becomes a matter of routine and the stratosphere starts to become more crowded, just as the troposphere and lower airspace is becoming crowded, we will do so from a position of data and knowledge. Thank you.
Thank you, Andy. Nicely done. So you've heard from Loon, and congratulations on the humanitarian work that they've been doing over the last several years. And thank you, Reinaldo, for pinch hitting for the Loon guys who weren't able to be here. I'm going to ask you to come back up in a minute and talk about Wing and how it is that you're sharing information and the plans forward for UTM and low to high. And Andy, I just want to congratulate you again on the great success that you had this summer, and very much appreciate the collaboration. In a very few minutes, you'll also hear from Stratobus, and Stratobus is to follow very quickly along in terms of dirigibles, as well as the great work that's happening here in China on dirigibles. So if you'll come back up here, Reinaldo, and talk about Wing and what you're sharing with Loon. And there was one question in the last panel that I wanted to ask, if you could please address as well. Someone asked, what about these open systems? What does that mean for security, and how can that possibly be safe? So if you can, just address that while you're here, that'd be great.
Thanks, Nancy, for adding that on, but I think it's a good question, and we can definitely talk through that. I want to start talking about low to high as part of that process based on the operations we discussed. Talking a little bit about low, and we haven't talked about this as much, but there's a huge range of operations in aircraft. I grabbed just a few of this from the web, but there's vertical takeoff tail setters, Mavic Pro, which you can buy here on the 3rd floor. You have the fixed wing SenseFly aircraft, which is very popular. Of course, Wing as part of a package delivery, and we have a winch on it, and that's a whole very different process than what you see on the right, which is DJI's new agricultural drone. But all these have different behaviors, different flight characteristics, different types of operations. And so we know UTM lower needs to support this wide range of types of flights that are going to happen, and the wide range and changing range of aircraft. And we talked this a bit to death, so I won't spend too much time here, but UTM does enable deconfliction for that full set of aircraft. It does it via cooperative data sharing. It does it because we have common situational awareness of flight intent, and it does it based on strategic deconfliction, based on the 4D trajectory and the aircraft performance that we talked about previously. And so as part of that, we looked kind of at upper a bit, and the various aircraft that are here, and we even include Boom as well. But these are all different. They're all going to behave very differently, and we're going to talk about both the wide range of operations, and you'll see more folks talk about it, but the wide range of aircraft and how do we support this diverse environment that's going to happen. I want to talk a little bit about Loon's flight planning capabilities. So what you see here is a balloon in the kind of upper left-hand corner, and all the blue lines are actually possible paths that the balloon can take with equal weight over 5 days. And so you'll see this probabilistic nature of trajectories as part of that. And that's a pretty far distance and a pretty far range. And it all happens with automation, looking at the winds and the probabilistic characteristic of winds. All that is kind of a machine level piece. But in addition, the aircraft performance can change based on the environment. how much sunlight it has, the winds that are affecting that aircraft, and even on a per specific vehicle level, right? The battery charge that the aircraft has, or the balloon has, goes ahead and can change its climb rate or descent rates, or even the balloon pressure might change how we want to go ahead and mitigate deconfliction as part of it. And so therefore you can kind of see that it's a very complex process, requires automation, and also requires the operator knowledge of where that aircraft is and what's on that aircraft and how it's behaving. Loon has done automated fleet management with self-separation, and here's a simulation here in fast time of various balloons kind of providing coverage to Kenya as part of that. But it's helpful to know that it's not just if a single balloon is complex. You can just imagine a fleet of balloons and providing that continuous service of what that is like for the operator, and that's something that the upper altitude UTM needs to be able to support. And so what are our learnings? So we saw the volume-based deconfliction on the right, and we talked about it quite a bit. But on the left, you can have that same process by taking the 4D trajectories and the multiple of them in upper altitude. You can apply very early on some probabilistic models of where that aircraft will be over time. And while it's a large amount of airspace and a little less precise, you can start having a good approximation of where that aircraft can be over time and utilize that and fit that into the UTM principles that we've seen before. So what can very high altitude learning happen from UTM? So strategic deconfliction and collaborative data sharing can be used for very high altitude, and this can be done at global scale. UTM supports that per specific vehicle, per specific environment performance that's required as part of that. It can be realized quickly, right, with a blend of strategic conflict detection and operator-operator managed deconfliction. If you look at the volumes on the previous slide and where the projection of where the Loon aircraft can be, you can go ahead and look at an hour, 2 hours out. You can determine if you're going to have a potential overlap with where Zephyr's operating. You could probably actually just call each other, given the amount of low volumes that exist there, and go ahead and figure out how you're going to manage that conflict. But again, having that strategic conflict detection enables that discussion to happen and that learning. And so Loon and Wing, we're collaborating with industry and very much with Airbus as part of this to realize UTM for very high altitude flights, and we're focused on doing this soon to support the ever-growing number of aircraft and balloons that are in the skies. That's it. Thank you very much. Oh, I didn't answer your question. So cybersecurity is a great, sorry Nancy, if you think about the systems that exist today, everyone equates UTM to the internet. And in some cases, it's not a great example from an aviation standpoint, but I do think it's a great example from cybersecurity. And I think in some cases that makes folks very concerned. I think Bill's presentation was wonderful on it. But for us, we're not nervous about security. I think part of that is, as a Google heritage company or set of companies, we know how to do security on the internet. We can leverage the best practices of both the financial industry and large-scale internet providers, and they're out there, right? We have strong identities. We have the ability for encryption. We have the ability to determine spam and other pieces. And so if you think about that standpoint in cybersecurity, we have done that well on the internet, but it does require good discipline, it does require good systems, and it does require vigilance. And so from that standpoint, I think it's a great question, but for us, we don't see that as a limiter for operations and something that we think industry can bring strength on as part of it. And I'll hand it back to Nancy.
Thank you, Reinaldo. So now we're going to move to dirigibles, which are really fascinating craft, I think, going forward. Brenden Hedblom is here. He's going to talk about Stratobus and also some work that Thales is doing together with Thales and Space. So Brenden, over to you.
Thank you, Nancy. And I believe we have a video. So, jump through the video with something? Yeah, if we could do the video first, that would be excellent. Thank you. Yeah, there's nothing like a video with dramatic music and no voiceover. So and so hopefully that gives you a bit of context of why Thales is quite literally in the space through the Stratobus. But in addition to that, Thales is also looking to bring our experience as a traditional airspace integrator to the table, in addition to the lessons we are continuously learning through the various approaches in exploring different solutions to UAS traffic management. And just like with UTM at low altitudes, we also need to establish at the very high altitudes where we are and what we need today to ensure that we have fair and equitable access to this airspace, where it is we are looking to go, what end state vision are we collaboratively working towards, and what incremental progressive approach is best suited to meet the operational needs of the system as it evolves. Now, at the early stage drivers for initial systems design, it can be broken up into really two main components. There's transitioning through controlled airspace and stratosphere operations. Now, in the ascent and descent phases through controlled airspace, it's important to be as simple and minimally intrusive as possible, so that these high altitude platforms are abiding by the existing ATM rules, while we're also minimizing the onboard equipment safety rules so that these often very lightweight aircraft are not burdened by additional onboard equipage requirements. So when operating at altitudes flight level 600 or higher, it's important that we foster an environment that's really promoting a collaborative airspace, has been voiced throughout the previous presentations, and is minimally complex, especially while operations are remaining at very low traffic density and at very low risk. This can be really done in the early stages by allowing autonomy of operations to these airship operators, such that when operating at these very high altitudes, we're not requiring them to receive authorization from air traffic control for any maneuverability at these again, high altitudes. In the early stages, this can really be done through trajectory-based operations, which is a very well-developed concept to enable that necessary situational awareness that can provide that self-separation, again, that's been kind of echoing from the previous presentations. In addition to that, we want to make sure that we have the contingency and abnormality management procedures in place for the identified use cases, such that if and when these high altitude platforms need to descend through the airspace, they're able to do so safely. Now, as been mentioned, that this technology very much is already here, and while the traffic density remains low, we're in a great, we have a great opportunity to begin building out these concepts and procedures, without really sacrificing any safety to the existing airspace structure. We're also in a great opportunity to be proactive in building out and developing this high airspace traffic management system, or high UTM, as the number of operations and the range of uses increase. Now, in exploring the various ways of how we might get there is, I think, where we can start drawing from those core principles and concepts that are emerging from UTM today. As with UTM, in establishing a high airspace traffic management system to address the growing number of applications in this airspace, it is important that we really seek to, again, establish what those core principles are, and make sure that those that are driving the development of the system, that those core principles are really more or less technology agnostic. As the airspace really is a shared resource, and we're going for a collaborative approach, that we have to make sure that driving these core principles is ensuring fair and equitable access to this high altitude airspace. Also, we want to be aiming to build off the existing construct, as interoperability will be increasingly more and more important, and that these low altitude and high altitude management systems are really stressing that from its inception. And also continuing to adopt that incremental, pragmatic, and feasible approach of a build a little, test a little will continue to be important as we seek to evolve off of those early stage drivers of initial system design. And just like UTM, there is a lot of emphasis on allowing the operational needs to drive the performance standards so that we can really avoid an overly prescriptive system from occurring, and trying to figure out how we can best balance the ways that the things that need to happen with how they do. And ultimately, again, continuing to build towards that one airspace picture, as we cannot afford to approach these as isolated environments anymore. So in applying the core principles from UTM to a high altitude traffic management system will be critical in really understanding how to build out the system in a way that's going to be addressing the growing demand of the airspace. This will be particularly important with the new high levels of automation and eventually autonomy to reconsider how we approach separation, deconfliction, and prioritization as in an airspace that's going to be lacking your traditional air traffic controller. Now, this will really elevate the importance of the data exchange models to really ensure that across all platforms that they're operating off of that single validated situational awareness picture. And again, finally, in working towards that one airspace picture, understand how these platforms will be interfacing with the existing air traffic management systems. So kind of in closing, trying to keep it short and sweet. The technology, as has been stated, is really already here, and we're able to operate in a way currently in accordance with the operational needs of the system. And so we have to be really careful moving forward not to hinder and impede that progress. But as, of course, density and risk eventually increase, we'll have to be, it's going to be hard to say for certain what will be required out of this high airspace traffic management system. So we'll need to make sure that we continue to let the needs of that environment really drive what that technology looks like. Thank you, that's all I have for now, and back to you, Nancy.
Thank you, Brenden. So by the time we get back wherever we go next year for Drone Enable 3, not only will we have completed tests from some of these products, we will have SORA output from some of these products, and we will have a framework for where we have a low UTM and a high UTM. So the next on the list I want to say is Dr. Xiao. I hope I got it right. He is the general manager for Beijing Infinite Space Technology Company Limited. And I have to say, I want to just really appreciate your willingness to come and talk about what's happening in China in the dirigible world. We're really looking forward to hearing about it. Over to you.
Thanks for Nancy's introduction, and I'm so excited sitting here this afternoon and listen to the presentation of my colleagues. And we're also excited about the collaboration with the Zephyr with the Loon. I think in few days in the future, we can get the collaboration in China with the Airbus or the Google. And for better presentation, I will make it by my mother language, so you can get the translation by English channel. 大家下午好，我简单介绍一下我自己。我是来自北京航空航天大学的。
My name is Xiao. At the same time, I also work as the General Manager of Infinite Space Technology Company Limited, which is doing the high altitude platform development. I'm very delighted and very honored to come here and to talk in this session to learn learn from UTM, the high altitude operation. My speech will include 3 parts. The first part will be about the work of our team and the work of China in high altitude platform. And the second aspect will be introduction to the features of the platform. And the third part, in terms of the high altitude operation, I will talk about what we can learn from UTM and what is the difference between its management and UTM management. In China, the high altitude platform development is actually done in the beginning of the 21st century, and one of the major projects is the CHEOS of China. In 2010, the government approved to implement the CHEOS, which will be completely activated by 2020 and composited by space-based system, near space, and airborne system, ground system, and application system, and the near space system mean high altitude platform system. And our work is greatly involved in the development of such a platform. As for our team, we started in 2006 in our research and development in the high altitude platform, and starting from 2010, we participated in this plan, and before 2015, our major concern is the prototype design and the breakthroughs in key technologies, for example, like solar cells and energy management and thrust system in high altitude and the control technology of the platform. From 2015 to 2017, we implemented 3 flight tests, and based on the tests, a great improvement is carried out. And starting from this year, our plan is that we're going to do some demonstration and testing of the application systems, including the telecommunication, remote sensing, and weather observation, and so on. And we plan to provide the production and service of high altitude platform from 2020. And for HAPS, we have many categories. Our major concern is the airships in the stratosphere. It's similar to the Stratobus of Thales, and our name is LKO1 for our platform. So the appearance is similar to traditional airship. In the front end, in the back of the airship, we have solar power cells, which will be connected to the avionics cabin, and one of the cabin will be used for the payload system, including communication payloads, space to ground observation payloads, and weather observation payloads. So the airship is like a balloon, and so when the vehicle arrived at the target altitude, it will be inflated to keep the full shape. Is the right image. You can see that on the right of the slide, and this is a test that we are doing, which is the airship ground test. Last year, in August last year, in Xinjiang province of China, we did a test of the flight. So this is the route-related flight test, which lasted for 19 hours. This is because of the restriction of the applied airspace use. We want to use this opportunity to share our tests and experience with the top companies in the regulation of high altitude aircrafts. The four pictures on the left are taken on the modules of the airships. On the right, it is the picture of the airship from the ground station. So the airship is flying in a stratosphere, you can see from this picture. At the same time, during the flight, we also work with the China Meteorological Administration, CMA, and we take the payloads provided by it and successfully carried four drop zones and obtained the weather elements such as the temperature, humidity, pressure, and wind profile from 18.5 kilograms altitude to about 3 kilometers. So we want to adopt the system to observe the tropical cyclone above the South Sea of China in the next year. At the same time, we also built a near space weather observation device through which we can gain the data on the weather. We have a short video to introduce the flight to you. So the airship is 79 kilometers long. This is the pictures of the sunrise taken on the airship. This is the test by the CMA. And also we did the test on the energy circulation and the verification of the thrust system. And this is the original test and the trajectory test. And we have also built to the ground observation system. So this is how we're doing in the flight. And now I want to introduce to you, based on our platform, our consideration of the characteristics that we need to have in the HAPS. So what are the similarities and the differences compared with UTM? We have three phases. The first one is climbing or ascending phase. For the ascent phase, we need authorities or departments to provide us with fine weather windows. And under the conditions, we will make the flight plan. The ascent speed is 3 to 8 meters per second. It can, when it reaches the anticipated altitude, it takes less than 1 hour. The second phase is the mission phase. The mission height is the mission altitude is 18 to 21 kilometers. The maximum air velocity is 22 meters per second. So the flight is based on the route with different with missions of different payloads. After the mission is accomplished, we will enter the descent phase. Usually it takes 2 hours. This is combined with the model of the airship and the wind profile. And then we do the simulation, and then we obtain the anticipated landing point. According to the landing point, we calculate the starting point at the height when we're flying. So when we begin to descend from this starting point, we can reach the anticipated destination. Usually, we will build the HAPS space in advance. In the space, we have various sound distribution and recollection device. We will distribute or send the airships. The airships will reach the expected altitude, and then it will go to the mission area to carry out the mission and the operations. The airship, we use centralized management. On the ground, we will have a comprehensive management system to gain the data of the operations of the airships. And for all the airships, they are managed comprehensively and uniformly. In terms of communication, communication is critical to the airships in the stratosphere. Just now I mentioned we use a centralized method. For a single airship, we use the ground control station and or the communication station or a moving communication vehicle to communicate with the airship. When the airship is carrying out BVLOS operation, we will also use related satellite for the communication. For multi-airships, we will build communication equipment on board, and we will set up the communication backbone network in the stratosphere. With this network, all the airships will become connected. We'll be able to identify the closest ground station, and then we're further connected to the control center for the uniform management. In addition, for the operations control of HAPS, it depends on its own onboard automation, on the gaining of data on the wind profile and weather. We can give the mission and then use the navigation algorithms to optimize the trajectory. And then we can have the airship flying according to the plan. For high altitude platform, it's unlikely to be controlled by individuals. So they need to be coordinated by the ground station. I think our colleagues have mentioned this point. For most high altitude platforms, they have the information identifiers. They have the user registration or user registry. And for low altitude UTM, they don't have such system. But in high altitude platform, this is a very good foundation. So through the control center, we can plan the flight trajectory. We can also monitor the operation status. We can also carry out contingency or emergency response plans. And compared with UTM, the high altitude operations are divided according to the flight phases. In the ascent and descent phases, because the platform needs to cross the ATM area or ATM space, including maybe some low altitude space of the UTM. So but the platform, but during the ascent phase, the automation of the system is not very good. So we need the permit or permission. And during the descent phase, we will also ensure the separation of UAS and manned aircraft. Currently, for the description of such a platform, ascent and descent are for these two phases, we need a base to ensure them. These bases are built in scatteredly populated areas, this is very convenient for us to do the distribution and recollection management for high altitude operations. Compared with UTM, the high altitude platform mostly uses automated control or beyond vision control. But based on our airship platform, its velocity is low or slow, and its size is very big. So for the radar on the ground or other identifying systems, these systems can be easily identified. So be it in some loss of control scenarios, it can be well regulated. In the mission implementation area, the platform needs to share share its information of its location and velocity with other aircrafts, including the coordinates, the altitude, and the time. So from these four aspects, we can ensure the safety of the airspace. In emergency, it can also interact with UTM or ATM for alertings. And for high altitude platform, usually it's long endurance operation. It can be several months, it can be several years, and its flying altitude is higher than the troposphere, so it should be different from the ATM and UTM. So of course, we need to integrate some of the management concept from the ATM side into the high altitude operation management, so that we can realize the full integration and the rational application of the whole areas of the space. And that's all for my introduction. And to conclude my presentation, I want to say that actually this symposium is held in Chengdu 10 years ago. We know that in Chengdu, in Sichuan province, we had a very severe earthquake. Actually, if back then our high altitude platform and the drones can be integrated into the UTM management, if back then we could provide such services, we may have lost less valuable things, because I grew up here. I'm a local, so I get quite emotional about what I'm doing, because I really want to serve the society with our technologies. Thank you very much.
Thank you very much, Dr. Gao. That was a great presentation. It's time for questions and answers, and I see I already have a couple. Thank you for that. Pour them in. So the first question is, how are the various panelists coordinating with the existing users above flight level 550 and airspace, NASA, Global Hawk, militaries, etc.? I can start that dialogue, but before I do that, let me reintroduce Scott Duffy. I asked him at lunchtime, just spur of the moment, to join us on this panel. Of course, you know him from CASA, and at least 3 of these guys are working directly with CASA in one way or another as part of a test bed there. So he's definitely one of the forward-leaning regulators, and I appreciate him being willing to engage with us this afternoon. So I can tell you from the Loon point of view that that is an ongoing dialogue, and in the ICCAIA, Upper Airspace Working Group, there has been dialogue with militaries around the world, and coordination continues and is ongoing. But you're absolutely right, that has been fundamentally the domain of militaries predominantly, and it won't be just these craft. There are others that are coming behind them, and also supersonics not far behind. So anybody else want to share a little bit?
The same, basically. It's about notification and collaboration, and I think for the time being, each individual operating region will be somewhat bespoke, but as higher airspace management becomes more mature, then there will become a standardized way of doing this, and hopefully everybody will join the higher airspace management club.
Anybody else? No, okay. They looked at me like, huh? Okay, so the second question is, today here we're discussing how high altitude UTM and high altitude ATM can learn from UTM. Do the panelists think that it's possible that in the recent future we'll learn adversely, since compared with low altitude, it's less dense, and high altitude, perhaps easier to manage. I actually think that's the beauty of what's happening, is that it is a low density, low risk environment to test out everything we've said we wanted over the years of 4D trajectory and trajectory-based operations and all of those things. So I think it's the perfect laboratory to do exactly that in a low risk environment. What I do think will be necessary for the high altitude operators is to work more in what has become a traditional RPAS kind of environment. So it's not these are not RPAS, and they're not small drones, they're something entirely different, and each one has its own characteristic, but certainly conforming to the SOAR process going forward, and others will be constructive and helpful. Anybody else want to take that?
Yeah, I think there'll be a lot of specific learning in the upper side, specifically because the aircraft are so different as part of that, and because the planning is much further, the amount of duration that you have to plan ahead is going to be much further than what you need on the ground for initial UTM operations, going from 30 minutes to an hour on the ground to multiple days in the air, and how you manage that. And the trajectories are going to be so distinctly different, and the vehicles operating at the edge of physics will be so distinctly different. And so I think there will be a ton of learning on that side, but that will be the complexity and not the managing the volumes of traffic, et cetera, as part of it.
Brenden, did you want to offer anything?
Yeah, I certainly want to agree with that as well. And I think one component that will be real, as far as what UTM can learn from the high altitude side of things, is specific around understanding how those negotiations are going to be taking place. Because I think with the high altitude, we're going to be seeing that more collaborative environment probably occurring much earlier. Because of so much low density and lower risk, it's going to be more readily enabled. So I think in how those negotiation standard procedures, how it ends up working out, will be a big component of what UTM can take away from it in the as that starts to develop ahead of the lower altitude airspace.
I guess the other thing that I would add is that these vehicles at this altitude are the most capable, with the best equipment, with the newest stuff, and thousands of pieces of information about health checks come off those vehicles a minute. So as you said when you were talking about Zephyr, there's just so much information available, and the long planning lead that allows for modifications in the plan to take place is pretty interesting. The third question is, so much is happening at lower levels. Is high altitude ATM really a priority for regulators? It's a good question, and I think, I'm going to ask Scott in a minute, but I have to tell you that I think that the regulators are suffering from what I call drone fatigue. Oh, speak louder? Okay. Oh, sorry. Really? That's rare for me, but okay. I think the regulators are suffering from drone fatigue, in that there's so much happening at the lower level. I think that's actually helpful at the higher level at this point. The work is ongoing and progressing really very, very quickly. So I think it's helpful. What is important in this sector is that the operators work together so that they come to regulators as a community, and they don't fuss with one another about very specific little details, but they work together on working as a community. That helps the regulators. So I'm hoping, and the plan is, that the regulators won't have to do that much in order to allow these operations to occur. Want to add to that?
I'd just like to say that we're very happy to bring a little variety to the life of regulators.
Thank you for the lovely question. I suppose the first part of that was, is it a priority? Yes, I believe the answer to the question is it's a priority for everybody. The fact that we're sitting here and we're talking about these projects, and they're operating successfully, and they're looking to move on to different phases and different developments. So I think the key to the success is going to be the harmonization. We will transition away from the them and the us. The layer cake model will actually introduce additional layers. And from there, the information that we learn as regulators and as operators and as manufacturers and all sorts of associations and education facilities, it feeds back into the system. And that's the key part that will help to improve the success for regulators to produce the right frameworks for people to continue to operate.
Very good. Another question, please elaborate, I'm going to give this one to you, on emergency procedures, technology, ATM, airspace design perhaps, if a high altitude flight has to descend below 600 if anything goes wrong. What your procedures?
Fundamentally, we rely on the long time constant of problems with craft like Zephyr. We will be able to predict anything short of a catastrophic failure, which we design out days in advance potentially. So Zephyr, for example, has got several hundred cells of batteries in it. If we were to lose a few of those, it would have no effect. If we were to lose a lot of those for whatever reason, it would have a detrimental impact on performance. But it wouldn't happen quickly. It wouldn't manifest itself as a very sudden loss of altitude. It would manifest itself in an evolution of the flight trajectory over a period of days, which will allow us to recover the situation and to work with ANSPs in order to do so safely by positioning the aircraft in a place where the necessary airspace bounds can be established in good order. There really is no need to rush into this, and that is the key to success, to managing safety.
And I can tell you from my experience, that's exactly what happens with Loon as well, as there's so many health checks that come off the balloon every minute that they know days in advance when the balloon is beginning to come to its final life, and they position it in a place that has low density and approval for landing as well. So I had a question. In Johnny's panel a while back, last session, he talked about how do you see what's happening now, what will it look like in 5 years? And I'm not sure we know in 5 years, but I think we can guess for next year. So next year and maybe the year following, where do you see, for example, in the university, where do you see your operations taking place, and what do you see happening in the next year or so?
我觉得在这个高空这个平台的这个研制方面呢，在最近几年呢，这个发展是非常快的。然后我们呢也是通过这个
And we have done a long term of experience accumulation, and we have collected valuable data from our tests during the past years. For the technologies of the platform, we have already made breakthroughs in the key technologies, and currently we are combining with some applications already to carry out the flight tests. I think maybe in the next 2 or 3 years, we are going to start the operation in some remote areas in China for the high altitude operation services. We are going to provide such services in remote areas, such as Loon of Google. At the first stage, we will provide communication coverage services, and then we also have some partners with which we are going to developing some tropical cyclone observation project. We are playing a very important role in this process. We use this airships platform to carry out weather observation and data collection on weather. In addition, I want to respond to one of the questions you mentioned just now. In fact, for high altitude platform management system, comparatively speaking, UTM system, I think, is more simple for me, because for low altitude, the density is very big and very high, and there might be interaction with the manned aircrafts. So, but in our high altitude airspace, it's very high in the sky, so maybe in the next 2 or 3 years, if we want to go to the application phase, our regulatory system must keep up with the trend. In this way, our platform and application can have the biggest play in this area. Thank you. Brenda.
For the next.
So I think in the next couple of years, for the Thales and Space Stratobus. I think that's more or less what we're planning on actually beginning to operate as well. So I'd imagine you're starting to see more other entrants as well, and starting to actually see when there might be multiple operators from different companies trying to provide services in closer proximity to each other. And as Reinaldo was saying, there are going to be different capability levels, so trying to figure out based off of how each one has their own restrictions for maneuverability, where Loon might have better control vertically, Stratobus might be able to maneuver better laterally. So trying to understand based off of those different vehicle capability levels, they all have those top of the line performance capabilities, but as far as again being able to understand how they're collaboratively working together and understanding based off of their own restrictions how you can do it in a way that again is not taking away that fair and equitable access to the airspace from either party. So I think over the next couple of years, where we start trying to see multiple service providers provide coverage in the same spot, is where we can start really exploring what that's going to look like.
Thanks for that. So we've come to the end of our time. I wanted to just offer a couple of thoughts about the way forward. So the barrier to entry for this sector is very high. So these are not companies that are fly-by-night companies. These are companies that have made major investments in not only their technology, but in their safety and in their safety systems. So I have extraordinary confidence in these companies, and those that are in this sector. I think this is particularly important. And secondly, I wanted to also mention that there's more work to do apart from just that in the technology. This is the area that we will be doing fleet management. So the one-to-many, how many is too many of the one-to-many? We don't know yet. So those are areas where we have to do more study, and we'll learn as we go along. But I want to thank particularly Australia and a number of the other countries around the world which are really leading the regulatory edge here and are open to this, not only technology, but open to collaboration and open to working through what is the right regulatory structure that's enabling the industry, but also continuing to support the safety. Does the 15 minutes here mean I have more time? Oh, you're telling me I'm done. That's what I thought. Okay. All right. Again, well, let's just thank the panelists. I thought you were trying to give me a message here. Let's just thank the panelists. And again, thank you for your candor, for your preparation, and for being willing to bring the future into reality. Thank you.
Yeah, thanks to Nancy and the presenters, and everybody please be back at 4 p.m. for the next session. We'll be pressing into the roundup. Thank you.